But luckily, only about half the class is ice boxes. And what I want to do today is show you the second way to cheat. So we don't have to do quadratics. I was looking at your book, and I sincerely hope that the homework that I assigned for next homework assignment doesn't include these, because your book has an awful lot of problems that require the quadratic equation. So I'm trying to find ones that don't, and hopefully I can find a fair number of them on the Achieve page. So, review from yesterday. First thing you need to do is make sure your equation is balanced. Then this thing that says write the equilibrium expression using the law of mass action. Ignore that last part. The law of mass action doesn't mean anything. It just means write the K expression. List your initial concentrations. Get your icebox set up. Put your initial concentrations in. If you have both reactants and products, calculate Q to see which direction it's going to go. Then put in your changes, plus X, minus X, whatever you need to put in. And then put the equilibrium concentrations as whatever the initial is, plus or minus X. Then substitute those into your K expression and solve for X, and then double check by putting the answer you get back into the K. So just as a quick review, this is one we did yesterday. 3 moles of HF, H2, and F2 are all placed in a 1.5 liter flask. So I need concentrations, not moles, so I divided 3 moles by 1.5 liters. Every one of them has an initial concentration of 2 molar. Then I had to find Q. I can't do this with reactants and products unless I know which direction it's going. So I put in 2 squared divided by 2 times 2, which gives me a Q value of 1, which is less than K, where K was 115. So if Q is less than K, the reaction is going to go forward. Like I said, I did this one yesterday. I just want to go through the steps again. So I put in the changes. If it's going to go forward, I'm going to lose H2 and F2, so I put minus X in each one of those. I'm going to get HF, but the balanced equation is H2 plus F2 goes to 2HF, so make sure you put your stoichiometric coefficient in front of the X, so it becomes 2 plus 2X. Then I'm going to put those into my K expressions. Oops. So 2 plus 2x squared divided by 2 minus x times 2 minus x. Now, the thing that we've talked about so far in terms of avoiding the quadratic equation is the perfect square law. This is a square on top and a square on the bottom. So to solve for x, I use perfect squares, which means I just take the square root of both sides. So the square root of 115 equals 2 plus 2x over 2 minus x. Square root of 115 is 10.7. Then bring the 2 minus x over to the left side and multiply through. I get 21.4 minus 10.7x equals 2 plus 2x. Move all the x's to one side and all the numbers to the other. I always move it so that my x's end up positive and hopefully my numbers end up positive too. So I moved the minus 10.7x to the right side to make it positive and move the 2 to the left side. So then I have 19.4 equals 12.7x, and my x is 1.53. Like I said, I did this one yesterday. I'm just reviewing all the steps. So put those in. H2 is negative x, F2 is negative x, so it's 2 minus 1.53. HF was 2 plus 2x, so H2 and F2 become 0.47, and HF becomes 5.06. So to double check, 5.06 squared divided by 0.47 squared is 116, which I told you yesterday is within precision of the 115 they give me for K. So that is the first way to avoid doing a quadratic, is to make sure that your numerator and your denominator are both squares, and so you can take the square root of both sides. This works when you have something like this, where a reactant plus a reactant makes two products, and the reactants have the same concentration. It will work anytime you have the same concentration. So the one that we did where CO plus H2O goes to CO2 and H2, as long as the CO and the H2O start with the same concentration, I'm still going to get squares. The problem is when I start with completely different values. So let's find a different way, something that's a little more complicated because I'm not going to get a perfect square out of it. So what do I do if it's not a perfect square? Benzoic acid ionizes in water to give H3O plus and C7H5O2 minus. The reaction includes an H2O liquid, which we leave out of the K expression. So my K expression is H3O plus times C7H5O2 minus divided by HC7H5O2. I'm starting with 0.1 molar benzoic acid, no H3O plus, and no benzoate anion. My K for this is pretty small. It's 6.3 times 10 to the minus 5. That's a pretty small one. When we get into the next chapter, this is a typical K value for an acid. And we'll be doing a lot of these. And there's a distinct advantage to most of these acids. There's two actually distinct advantages. So I put these into my ice box. And I have 0.1, 0, and 0, minus X for my acid, plus X for both my H3O plus and my anion. So I have 0.1 minus X, X, X. When I put this into my K expression becomes X times X over 0.1 minus X. That is not a perfect square. If I multiply both sides by 0.1 minus X, I'm going to end up with a quadratic. So what can I do to not have a quadratic? Well, the fact that the K value is 6.3 times 10 to the minus 5 indicates I'm not making a lot of product. So I'm going to make the assumption that the amount of product I make is so small in comparison to the 0.1 that the concentration of the benzoic acid doesn't actually change. So instead of using this quadratic, to avoid the quadratic, my cheat code is that when K is very small and little product is created, I can drop the minus X from the 0.1. I'm going to assume that the 0.1 is so much larger than the X I would create that it's not going to make a difference. So if X is small, I'm simply going to drop the X. I'm not going to drop the X when it's only X. I'm not going to do that, but I'm going to drop it when it's a minus X from my reactant. So when is it okay to drop the X? The rule is that if you ratio the initial concentration by the K value, and it's greater than 1,000, it's probably okay to drop the X. 0.1 divided by 6.3 times 10 to the minus 5 gives me 1.6 times 10 to the third, or 1,600. 1,600 is greater than 1,000, so I've rationalized I can drop the X. So I'm simply going to get rid of that. When a K value is very small in comparison to the initial concentration. Now this only works if I've got an initial concentration that's large enough. If I had used 0.01 acid, I couldn't drop the X, because then I would only be off by a factor of 160, not 1600. So I need the initial concentration to be quite a bit larger than the K, and then I can just drop that minus X. So now 6.3 times 10 to the minus 5 simply becomes x squared over 0.1. Now this is the other advantage of the acids we're going to do in the next chapter. One, we can normally drop that x, and two, the numerator is always x squared, no exception. When we're doing a dissociation of an acid, we're always going to have x squared in the numerator. So I now have x squared over the initial concentration. That's all this is. And for most of the acids we do next chapter, that's exactly what it will be. It will simply be, oops, where did I flip? It will always be x squared over the initial concentration. That's actually going to make our K values in the next chapter a whole lot easier to deal with. So move the 0.1 to the other side, multiply both sides by 0.1, and x squared becomes equal to 6.3 times 10 to the minus 6, and x becomes 2.5 times 10 to the minus 3. So back into the icebox. I'm leaving my reactant at 0.1, and my products are 2.5 times 10 to the minus 3, both of them molar, because those two things always have to be equal in an acid. Now, there is a check to see that it was okay to drop the x, and that is how large is that x value compared to the 0.1. Was it correct to drop the x? Well, if it was correct to drop the x, then I want the x value to be less than 5% of the initial concentration. So if x is less than 5% of the initial concentration, then I'm okay dropping the x. So once I drop the x and I solve, I want to double check that I was correct in solving. So 2.5 times 10 to the minus 3 divided by 0.1 times 100 to give me a percentage is 2.5%. That's under 5%, so perfectly acceptable to have dropped that x. So the first thing you do is look to see what the ratio is between the initial concentration and the K value. If it's over 1,000, drop the x. When you're done, double check that that was okay. So this works anytime we have a low K value. This one happens to be for an acid, and most acids will always be x squared over the initial concentration because their Ks are low enough to drop that x. But that may not be the only time we want to look at dropping the x. Nitrogen and oxygen go to NO. My Kp is 2.5 times 10 to the minus 3. Looks like it's low, but if I do my ratio of the initial, in this case, pressure to the K, whoops, I'm going to find it's not over 1,000. So I have no NO here. I have 1.3 atmospheres of N2 and 0.7 atmospheres of O2, so I'm going to put those into the icebox. And I know that there's one N2, one O2, and two NOs, so the change in NO will be plus 2x. Each of these will be minus x, and the question is, can I drop those x's? Can I avoid the quadratic? Well, not only would this give me a quadratic, but I have to do that whole foiling thing of 1.3 minus x times 0.7 minus x. Really would like to avoid doing that. But when I do my ratio, I do it to the smaller atmosphere, and it's only 280. It's not over 1,000. But I'm going to try it anyway, because if I can avoid the quadratic, I want to. So I'm going to go ahead and drop the x's anyway. So I'm going to put in x squared over 1.3 minus x, and I'm simply going to get rid of those minus x's. My test shows that I am not high enough to guarantee I can do this, but let's try it. So now I have 0.0025 equals x squared over 1.3 times 0.7. 0.0025 times 1.3 times 0.7 gives me x squared is equal to 0.002275. Square root of that, 0.048. The question is now, is 0.048 less than 5% of my initial pressures? So these are what my final concentrations look like. 1.25, 0.65, and 0.096. Sorry, microphone unpumped. So is x less than 5% of the original value? Now I have two different original values, so I have to compare it to both. So 1.3 minus 0.048 equals 1.25. That 0.048 divided by 1.3 times 100 gives me 3.7%. I'm under 5%, but that's for the larger of the two values. When I do 0.7, and 0.048 divided by 0.7 times 100 is 6.8%. It was okay to drop the x with respect to the N2, but with the O2, it's actually over 5%. So technically, dropping the x wasn't correct. I could have dropped the x only for the N2, but I can't drop it for the O2, and if I can't drop it for the O2, then I still have kind of a mess, because I will end up with 1.3 minus x times 0.7, which means I will have an x squared and an x, which means it needs a quadratic. So unless I make a mistake on the test, all of these should be under 5%. I will not give you one, like I said, unless I screw up on writing the test, I will not give you one that requires a quadratic. So if you can drop the x and then double check, all of these double checks should be less than 5%. Okay. So these are our two ways to avoid the quadratic. One is using the perfect square, which only works when you have exact amounts of reactant and no products, or you have exact amounts of reactants and two reactants make one product, so that that becomes squared. The other one is when your K value is very small. And if your K value is very small, then start by dropping the x's in your reactants. We want to, at all cost in a test, to avoid dropping, or to avoid having to do a quadratic. Okay, this is H2 plus I2 goes to 2HI. If I start with initial concentrations of H2 and I2 that are equal, this should be a perfect square. But suppose I start with different amounts of H2 and I2. HI doesn't matter because that's going to become a square on the top. So that will be a square, but what happens to my bottom? My bottom becomes something that's not a perfect square. So first thing I wanted to do was figure out whether it was going forward or backwards. My K value is 54. My Q value is 69.7. So Q is greater than K. So my reaction should go in reverse, which means my positives go on the reactant side, my negatives go on the product side. My K value is 54. There's no way I can drop an X. So I put these into my K value, and I can't solve this without a quadratic. Because my initial concentrations of H2 and I2 were different, even though my top is a square because I have two HIs, I cannot solve this without a quadratic because my initial concentrations of H2 and I2 were different. K is too big to drop the X, and this is not a perfect square. So no way to solve this except doing a quadratic. And not only a quadratic, but foiling the bottom, squaring the top, bringing the bottom over to the other side. I could give you one question like this for a test and expect you to have it done in the amount of time I give you for the test. So again, we're looking for things where the initial concentrations are the same and the top is a square, the numerator of the product is a square of some type, or we're looking for a very, very small K value. Sorry, I wanted to see where I was with respect to, yeah, okay. So I did the quadratic, I solved for X, and I did get an X value, 5.25 times 10 to the minus 4. But you won't be asked to solve a quadratic. Okay, so ice boxes. Ice boxes are seriously the majority of what your next test is going to be, because your next test is on chapters 15 and 16. As I said, 16 for the most part is easy. Your ice boxes should all end up with X squared over the initial concentration. We'll get to that on Monday. But ice boxes, look for the perfect square, look for a very small K value, or write on the test, this needs a quadratic, I can't solve this, why did you do this to me? Like I said, Dr. Cadu made a mistake once and ended up with something that was a quadratic because when they did the is X less than 5%, it came out to be 20%. Students were not happy. Even if you have a graphing calculator, it can be difficult to solve that quadratic within a reasonable time. And Dr. Cadu's exams are only 15 minutes long. So I'm not going to put a quadratic on the test. Okay, that is the end of ice boxes for chapter 15, which makes it look like, unless you want to do more practice problems of ice boxes at the end of class, we'll probably get out of here early. It is a Friday, you might want to get out of here early. Gabrielle's going, yeah, I'm happy getting out of here early. We're moving into something else. We're moving into something called Le Chatelier's principle. Okay, I've been told it's pronounced Le Chatelier. He was French. I took French twice. I flunked French twice. I did much better in German and Russian. The Romance languages were just way over my head. So if you speak French and I'm mispronouncing it, I apologize. Now this says relieving stress since 1884. What the heck does that mean? Well, stress is anything that we do to a system at equilibrium that messes up the equilibrium. So Le Chatelier's principle says that when a system is at equilibrium and it is stressed, it will respond by shifting to reduce that stress. So whatever we do to it when it's at equilibrium, it will change itself until it gets back to an equilibrium with the new changes that you've done? Well, there are multiple ways that we can add stress to this. So we're going to look at a variety of ways that we can add stress. The first way to add stress is to change the concentration of something. We can add a reactant, we can add a product, we can remove a reactant, we can remove a product. So in this case, in A, I had an equilibrium. Again, we're looking at that Haber process. I have an equilibrium, and then they added more N2. I start with some balance with a fairly small amount of NH3 produced. The K value for this is not great. So I add more N2. You can see the first dark blue column increases. The H2 stays the same. And when it shifts, it wants to shift to a new equilibrium, and I have more NH3. Adding that extra N2 forces that N2 that I've added to react with H2 and make more NH3. And this Haber process, as I said, does not have a great K. We don't get a lot of NH3 out of it. You want to make ammonia, this is exactly what they do. They let the system come to equilibrium and pump in more N2. Let it come to equilibrium, pump in more N2, and you get more and more NH3 out of it. So adding a reactant will always cause the reaction to go forward to use up that reactant and create a new equilibrium. So I had a K value. Oops. My 3 is supposed to be an exponent on the H2. When I started with a set of initial concentrations that were 1.52, 2.05, and 1.56, my K value is equal to 0.297. That cannot change. K is a constant. I cannot change that. So when I add N2, and I increase it to 3.51, now if I do a Q value, my Q is 0.173. I'm no longer at the K value, so I'm not at equilibrium anymore. And Q is now less than K, and when Q is less than K, the reaction moves in a forward direction. So the stress I'm adding is more reactant. That stress then makes my K value a Q value because I have too many things down in the denominator now, and it will shift forward to create a new equilibrium where K, 2.97, 0.297, has to remain the same. So an increased amount of N2 will react with H2 to lower the concentration of H2 and increase the amount of product. In general, if I have a situation where I increase one of these guys, it will decrease the guy that's on the same side of it and increase the guy on the other side. So the addition of the N2 decreases the H2 and increases the NH3. It decreases the thing that it's on the same side with because it's going to react with that, and it's going to increase the one on the other side because that is what it's now creating. Now, I cut this little jokey thing out because I love bad science jokes. Le Chatelier's principle: if a stress is applied to a system in a dynamic equilibrium, the system will adjust to relieve that stress. Somebody didn't like that homework, they're throwing it into the fireplace. Can't do that when I give you online homework, sorry. So I reach a new equilibrium now. So I started with equilibrium. I added N2. I now have a Q of 0.173. It reacts until I get the equilibrium again of 0.297. Now, my NH3 has gone from 1.52 to 1.64. It's gone up. My N2 I added, so that was 3.51 to start, but as that reacts, it will go back down. So it's now 3.45. And H2 goes down to 1.38. So you can see N2 goes down by a very small amount, but NH3 goes up by quite a bit, and H2 goes down by quite a bit. This is Le Chatelier's principle for adding a reactant. Now, I could do the same thing. I could do the exact same thing. Let me create a new slide here so I can write on it. Okay, so if I have N2 plus H2 goes to NH3, adding either N2 or H2 causes it to go forward. I'm adding reactants, it will push it forward. Adding NH3 would send it backwards. Again, my Q would now be different. I've got more in the numerator, greater than, Q becomes greater than K, it will shift it backwards. Now, one way for industry to fix the Haber process is to just keep dumping more into it. It works. But at the same time they're doing that, they also remove the NH3 that's there. Because anytime I remove something, it needs to shift to fill in that hole. So if I remove NH3, now I've got lower amounts of NH3, I've got a smaller numerator. The reaction is going to go forward to fill in the hole I just created by removing NH3. Or if I remove N2 or H2, it will move to fill those holes and move backwards. So I can add a reactant to product, or I could remove a reactant to product. And constantly flowing N2 into the system and at the same time removing NH3, which has a higher density than N2 or H2, so it sinks to the bottom, so there's a little valve down at the bottom of my setup, keeps this constantly creating more NH3. It's how industry can create the amount of ammonia that it does for commercial uses. So adding anything shifts it to the other side, removing something shifts it to the side that you removed something from. So what happens if I increase the amount of Cl2? I'm now increasing the amount of the product. It's going to increase my numerator. My Q will become greater than K. And when Q becomes greater than K, the reaction will want to go backwards. So adding something, it's going to want to go the opposite direction. So it's going to shift away from the Cl2 toward the reactants because Q becomes greater than K. Now, if I decrease the amount of NO, now it's going to have to shift to the side to fill that hole I just created. And it's now going to shift toward the products because now Q is less than K. Removing NOCl has to shift to fill that hole. My denominator is going down. So when my denominator goes down, my Q value goes up. And so again, Q is greater than K, and it will shift toward the reactants. Okay. This is a typical type of question you would be asked on the multiple choice part of the exam. Which direction does the reaction go when I do the following? I can put it on a long answer test, but then I would give you a chart with multiple things like this saying, what happens if I do these things? So this is an example of what happens with Le Chatelier's when I mess with concentrations of a system that is already at equilibrium. Now, when I have a Kp and everything is in pressure, then changing the pressure will make a difference. According to our stoichiometry, if I increase the pressure, the system is going to want to move to the side that has the smaller number of moles. It gives these things more room to spread if you have a smaller number of them. So if I increase the pressure, it's going to shift it to the side that has the smaller number of moles. And we're doing this when we only have gases. So the picture, again, is the Haber process. There are 4 moles of gas on the reactant side, 1 N2 and 3 H2s. There's only 2 on the product side, NH3. So if I increase the pressure, it's going to want to shift to the products that has fewer moles of gas. So this is NO2 going to N2O4, 2 moles of gas on the reactant side, 1 mole of gas on the product side. So you can see as I increase the pressure, I get more and more of the N2O4. So again, back to the Haber process. What percent of mass of ammonia do I get when I'm mixing N2 and H2 in equal quantities? At 300 atmospheres, I get 48% NH3. 300 atmospheres is a lot, but these are done under pressure. But when I increase it to 400 atmospheres, I get 55%. And when I increase it to 500 atmospheres, I get 61%. So I can see that the picture I showed where increasing the pressure created more NH3 because there's fewer moles of gas on that side can be seen. I have less of the N2 and H2 and more of the NH3. Now there are 3 things there because we're going to come back to this chart and we're going to see those are at 3 different temperatures. So I just wanted to look at the pressures. But you see for every single one of them, no matter what it is, the value at 500 atmospheres is larger than the value at 300 atmospheres. Okay, now what about changes in volume? In every one of these things I looked at, I changed the pressure by changing the volume. And according to Boyle's law, pressure times volume is a constant. So if I increase the pressure, I decrease the volume, so a decrease in volume will work exactly the same way as an increase in pressure does. Because most of the time I'm increasing the pressure by decreasing the volume. So I can change either the pressure or the volume, and it will always be that smaller volumes give me higher pressures, which give me more of the side that has fewer moles on it. So I increase pressure here by decreasing the volume. So an increase in pressure was a result of the decrease in volume. So increase the volume if delta N is less than 0, which means there are more reactants and products, it will shift it to the product side. Decreasing the volume will shift it to the reaction side. If delta N is equal to 0, if I have something like H2 plus I2 makes 2HI, changing the pressure or the volume does not change anything. So H2 plus I2 goes to 2HI is unaffected by the changes in pressure or volume. Because PV equals nRT, our ideal gas law, does not say anywhere in it what are the molecules that are in there. PV equals nRT is independent of the type of material you have. Now, if I have more products than reactants, increasing the volume will give those reactants more space, and it will shift more gaseous products than reactants. Increasing the volume should shift it to give those guys more space. Decreasing the volume should shift it to the side that has fewer molecules of gas, and therefore would shift it to the reactants. So H2 plus Cl2 goes to H2HCl. There is no change because the delta N is exactly the same. 3C2H2 gas goes to C6H6 liquid. C6H6 isn't even included in my equilibrium because it's a liquid. If I increase the volume, I will allow more space for that gas, and I will allow more gas to form. Water, H2O, can evaporate. It goes from the liquid state to the gaseous state. If I increase the volume of the container, it's actually going to evaporate faster because I'm going to be able to get more into the vapor state because there's more space for it to move around. If I decrease the volume, I literally push the gas molecules back into the liquid. And I get fewer gas molecules out. So this works for things other than something like acetylene, which is a nonpolar gas. It works for any gas, and in particular, water. Water evaporates depending on what is the outside pressure, what is the volume of the container that it's in. I know you wouldn't notice because it's humid out, but air pressure is actually lower during a rainstorm than it is on a nice day like this. You wouldn't want to put the water into an evaporation situation where rain's going to get into it, but if it's in a sealed container, it will actually evaporate more on a rainy day than it does on a sunny day because the pressure's a little bit lower. When they give you that weather map and they say L or H, they are literally talking about what's happening to the air pressure. It goes up on a nice sunny day, it goes down on a rainy day. So this would switch towards the reactants where I have more space for the gas. C plus H2 goes to CO plus H2. Please note that the carbon is a solid. So the carbon is not part of it. So it's going to shift towards the products where I have 2 moles of gas that want to take up more space than the H2O. Now, this is one that we've had arguments about in the department. What happens if I change the pressure by adding an inert gas, one that cannot participate in the reaction, one that is not a reactant or a product or a catalyst or something like that? I just pump something like argon into the system. Argon may get in the way of the reactants finding each other, but it doesn't affect the actual equilibrium position because when the particles do find each other, they're going to reach equilibrium. So the addition of an inert gas increases the pressure, but that pressure actually pushes the particles together, increases the number of collisions, but the collisions with the inert gas don't cause reactions and leave the equilibrium intact. This is an argument we have because there's a guy that works over in Science 1 who insists that adding pressure no matter what will shift it to one side or the other. Inert gases will cause things to collide more, but since those increased collisions are with something that does not react, it should not change your equilibrium. So I have nickel monoxide. It goes to nickel solid when it's heated and releases the carbon monoxide gas. What happens if I add neon to the container while I hold the volume present? Well, neon isn't in that. Neon is an inert gas. It's not a reactant, it's not a product, it's not a catalyst. So adding neon should do absolutely nothing to my equilibrium. What happens if I increase the volume of the container? Well, I have 1 mole of gas on the reactant side, and I have 4 moles of gas on the product side. So increasing the volume should shift it towards the product. Now what happens if I add more nickel? Think about this. What happens if I add more nickel metal? Does it shift the equilibrium? Gabrielle says no. Why not? Xavier says no. Why not? Because it's a solid. Changing the quantity of a liquid or a solid does not change the equilibrium because it's not part of the equilibrium constant. So adding more metal will do nothing to this. So, recap, concentration and pressure, or if we want to also say volume, would be inverse to pressure. So increasing the concentration, increasing the pressure, or decreasing the volume of the reactant will shift it to make more products. Because I'm pushing things together, I'm getting more reactions that will go forward. Decreasing would be exactly the opposite. Now, if I increase the concentration or pressure of the product, decreasing the volume, now I've got more product, it's going to shift it backwards to the reactants. This is all of Le Chatelier's principle in terms of changing pressure, volume, or concentration. Just, if you add something, shift it to the other side. If you remove something, shift it to the same side. Adding pressure or decreasing volume shifts to the side that has fewer numbers of moles of gas. Now, the other thing that we could change is temperature. Now, temperature is going to be different because rate constants change with temperature. And if rate constants change with temperature, then I have a situation where my equilibrium will shift, but it shifts depending on whether heat is considered to be a reactant or a product. So to determine how temperature affects equilibrium, I need to know whether the reaction is exothermic or endothermic. If the reaction is endothermic, I treat heat like any other reactant. Adding heat will shift it towards the products. Now, logically, this makes sense. If I have an endothermic reaction, it wants heat. If I increase the temperature, it's going to go better. So if the reaction is endothermic, and I treat heat like any other reactant, increasing the heat will shift it toward the products. So the reaction becomes easier as the temperature increases. Okay, this is the reaction of N2O4 breaking down to 2NO2. We could do it backwards, which is what I've got in the picture. The picture I actually have NO2 going to N2O4. I mentioned before that NO2 is that nasty brown haze that large cities get during rush hour. Over time, however, because this is endothermic, as it gets hit by sunlight and the temperature increases during the course of the day, we shift to producing more N2O4. The brown color disappears. Now, if this is exothermic, it's releasing heat. And when it releases heat, heat becomes a product. If the reaction is exothermic, we want to treat heat as a product. Now, releasing heat, I've mentioned this before when we talked about enthalpy. When you sweat, it's harder to release your heat when it's hot outside than it is when it's cold outside. The same thing is true for a chemical reaction. It's harder for it to release its heat when it's trying to release its heat into a hot surrounding. It's easier for it to release its heat into a cold surrounding. So if I'm adding heat as a product and I increase the temperature, it's actually going to shift it backwards. The reaction becomes harder to do at higher temperatures. And temperature changes change the rate constant. That's the only thing I can do that will change rate constants. And because it changes rate constants, and equilibrium constant is a ratio of the rate constants, it changes my equilibrium constant. Rate constants, equilibrium constants are constant as long as you keep temperature constant. If you change the temperature, they will change. And they will change according to whether or not the reaction is exothermic or endothermic. So in this case, I've got that ammonia synthesis, which is endothermic at 500 degrees. My K is 90, which means I have a lot of where's my, I thought I had the ammonia synthesis here. Making ammonia is endothermic. It does require heat to do. As I increase the temperature, my K goes down. My K going down makes the reaction easier to occur. So, no, that's not what I said, harder to occur. This can't be for the ammonia synthesis, because ammonia synthesis is endothermic. I took this out of the book. Ammonia synthesis reaction as a function of temperature becomes harder as temperature increases. But making ammonia should be endothermic, not exothermic. Okay, well, this assumes then the reaction is exothermic, which means the book is confusing me. So, reaction becomes harder to do as the temperature increases because the reaction is exothermic. So, this is supposed to be the reaction. NH3 goes to H2 plus NH2. So how is K affected by the increase in temperature? To do this, I needed to know what the delta H was. And as I said, this is an endothermic reaction. It is plus 46.2. So this requires heat. So endothermic should increase heat, which is why this chart can't be for the ammonia synthesis. This has to be for the ammonia decomposition. Because as I increase the heat, I'm going to create more of these products. Because it needs the heat to react, so I'm going to create more products, which will increase my K value by increasing the numerator. After I change K, if I increase it by increasing the temperature, it's going to move towards the product. And the partial pressures will decrease the amount of NH3 I have and increase the amount of H2 and N2 that I create. Okay, so overall, looking at an endothermic reaction, adding reactant shifts it to products. Adding products shifts it to the reactant. So when I say it shifts it to the right, that shifts it to the products. When I say it shifts left, it shifts it towards the reactants. Removing N2O4 needs to fill in that gap, so it moves towards the reactants. Removing NO2 moves it to the products. Adding HE, helium, makes no difference. Decreasing the volume will shift it towards the reactants because there's only 1 mole of gas there. Increasing volume will shift it towards the products. Increasing temperature will shift it toward the products because it wants that heat. And decreasing the temperature will shift it to the left. Now, as I said, a question on a test would either be a simple question as, what will changing this one thing do to the overall reaction? If I run out of things to put on the long answer part of the test, the chart would look exactly like this. Tell me what happens in each one of these cases. and you get multiple cases. Whether or not you get this as a multiple choice or you get it as a long answer depends on how nice I'm being about how many ice boxes I put on. If I want to put on one less ice box, I would put up something like this. Okay, catalysts. Catalysts change the rate constants. Catalysts take a single-step reaction and turn it into a multi-step reaction, and therefore speed the reaction up. It just means it gets to equilibrium faster. It does not affect equilibrium. Catalysts have no effect whatsoever on the equilibrium of the system, except for the fact that you get to equilibrium faster. Okay, so it's 10 o'clock. This is where I would normally take a break. So you have two choices. We can take a break, and I'll come back and I'll work some more ice boxes, or you can all go home a half an hour early. If you come back in 10 minutes, I'll work at ice problems. If you go home, have a good weekend. It's supposed to be a beautiful weekend. Enjoy it. I'm going to the beach. Okay.